6.4, volume by shells. What we're going to have now is another method of finding volume when we have more issues to deal with, such as it's not an easy one to integrate by some disk method or washer method. This method then says if we had a bunch of cylindrical shells or just like pieces of paper that we had at different heights that matched the function or the curve, and then we kind of just layered them up and made a mass to fill the volume, we can find the volume in that way by unwrapping each piece of this shape. So here's this one that we were doing here, this outer shell. If I was to take that and unwrap it, we have, remember, volume of it would be height times length times the thickness of it. So if we have height being the function, because it's from wherever we're going to the function, whether it's between two functions, f and g, or from an axis to the function, we can say the height is f. And we're going to say f of some k. The length of it, because it was a circle, it was a circumference that we unwrapped, it's going to be 2 pi r. But in this case, we're going to have 2 pi times x. That's for where that x value on the x-axis that we decided to use that to find this height. And then we always have the thickness being delta x. And remember, the whole point of integration is to assume that the delta x is taking the limit as it is approaching 0. So we want no thickness on this shell when we're going to sum them up. So we have here a couple pictures, one with a bunch of shells and this other one here where I have drawn this blue line. So this case in this drawing, we can see it's rotating around the y-axis, but I'm going to be integrating for this length here. Remember, I said I'm trying to find this height. So this is now we're going to always think about in shell method. We're going to not think of the radius around the axis we're rotating for revolution. We're going to do what's perpendicular to the axis, keep saying that, the axis that we're rotating, we're going to do the perpendicular height. So we want to go ahead and we're going to use this formula, the shell method. We're going to have the volume from A to B, 2 pi x. Remember, that's our length. Our height would be between two functions, and then we're going to have times our thickness, dx. And then remember, this is another reason why we might want to do this. I have a good case of the bead here that I have drawn, that it could be a cylinder that was drilled through the center and we want to find the volume of this bead. This is a case where you're going to want to try to do shell method because our other methods would not work. So let's go ahead and do some examples. I have number 5. We have here that it's rotating around the y-axis. We were given the functions, the region being bounded by y equals x minus x squared and y equals 0. So this is a case where I'm definitely going to have this as my height, but my f of x function is the curve, and my g of x function is going to be the x-axis, or it's 0. So using this formula, so rotating around the y-axis, terms of x, my bounds are on the x-axis. I'm always going to have this constant 2 pi, so I'm going to always have that out front of my integral. So then I'm going to go ahead and I have set up that we're going from 0 to 1 because I found where the graph intercepts the x-axis, setting up my x times my function, simplifying the equation, and then I can find the antiderivative now. So my volume is going to be 2 pi times the antiderivative, and we're evaluating from 0 to 1. Remember, when you have a 0 bound for your lower bound, that's nice because it's always going to be 0, and plugging in my upper bound into this equation, I need to make a common denominator, and then I could do my subtraction so that I really end up with pi over 12, and I'm sorry, not pi, 1 over 12, and I get pi over 6 as my answer. All right, doing another one. I have number 7. So again, we're rotating around the y-axis. So that means my height is this here between these two functions. My f of x and then my g of x would be 0. They gave us that we wanted to stop the region at 2. So I know my bounds are from 0 to 2. Now this is a case then when I go to set this up and I want to take the antiderivative of it, it's too messy. I see an extra x in this, that means I'm definitely going to do a u substitution. So I'm going to do a u substitution of 1 plus x squared, taking the derivative and moving my dx over. I then have to remember I don't have an extra 2 in my equation to replace, so I have to divide both sides by 2. Doing my substitution then, I see that I can replace the 1 plus x squared with u. I'm going to replace dx times x with du over 2. But because that over 2 I can pull out as a coefficient of 1/2, I'm going to go ahead and do that. Last thing is remember, in order to save myself some extra steps, I'm going to do new bounds. So when I put in my new bounds, my lower bound is now 1, and my upper bound will now be 5. So I'll be going from 1 to 5. This then reduces. So my integration will be of this, and we can go ahead and evaluate it. We have to remember that the antiderivative of 1 over u is ln of the absolute value of u, and we're going to evaluate it from 1 to 5. This then, you have to remember some of your log rules that when we plug in our bounds, we see that this value, anything that is base has an answer of 1. It means its exponent is 0. So this evaluates to 0. And then my answer then finally is pi times ln of 5. So then moving on, we'll do another one. I have 21. Now we're going to go about the x-axis. So if I'm going about the x-axis, you then know that we have this as my height. So this is my height that I'm going to evaluate. We're going to do it by shell method. So I'm going to have the 2 pi, and our bounds then are going to be from C to D, and in terms of y. So from C to D, I'm now going to go from 0 to 3, and in terms of y. So I'm going to have y as part of my length, the 2 pi y, and I'm going to multiply by my function. Remember, it's supposed to be in terms of y, and it's already set up that way, so it's y squared, and then dy. So finding my antiderivative of y cubed should be y to the 4th over 4, and evaluating it from 0 to 3. Now, we could save ourselves this step by pulling this 4 out, and we really have pi over 2, and we're going to evaluate y, to the 4th power, and I'm just going to plug in my upper bound. I keep changing that, sorry. And I should get then 81 pi over 2 as my answer. So we could keep moving on with examples of that, but I wanted to give you one that has a g function in it. We've done something that has always had the g function as 0. So let's do number 29. I'm given, oops, sorry. Let me read the problem for you. Number 29. It says that we want to find the area by the solid formed when a hole of radius 3 is drilled symmetrically along the axis of a right circular cone of radius 6 and height 9. That's all this problem tells us. No equation or anything, but a right circular cone. So we're going to draw one. So I have a right circular cone, and basically it said that it was a radius of 6, so my R here would be 6, and a height of 9 is 9. And that they drilled a symmetrical center through this that had a radius of 3. So we had a radius of 3 being drilled through. So that means this is my area of integration that I want to find when it's spinning around, and we're going to go ahead around the y-axis. So we're definitely going to do shell method with this. That means I need to find my f function and my g function. So what is nice because of this cone shape, we have a linear line. I'm going to go ahead, I've got 2 points that I can find the slope of the line, or you can go off the graph, and we can see that it's -3/2. We're going down 9 to the right 6, so setting up 9 over 6, -9 over 6. We can reduce by 3. That's my slope. We have x, and we have a b or y-intercept of 9. So there's my f function. In this case, remember we're going around this axis, so this is, or we could call it, I'm sorry, not f function, let's call this the p function, p of y. So then we're looking for the q of y, and then that would be this right here. So the only problem is that I really don't have a function there to plug in. So what do I have to do then in order to figure out this volume? This then is not necessarily anything I could do that way. I'm going to have to just say, well, this is my function, and maybe I can't do this way. Maybe I'm going to have to do it some other way. So I'm going to go ahead and we're going to calculate it from different bounds instead of going from 0 to 6. It's not, we're going to go on the x-axis. So really, in a sense, I'm only going from 3 to 6 on my bounds. So this does not have a g function after all. We are going to call this then, in this case, the f of x function. We're going to have our volume being 2 pi. We're going to go from 3 to 6. Remember, we have x. So we need terms of x, plugging in our function, dx. All right. So even though I had this hole, and because it was rotating around this axis, the y-axis, it did not technically have a g function for us. It had just the bound change. So then we're going to go ahead and we'll simplify this up and we'll evaluate it. Now, it does make things much harder and messier, so I'm going to simplify this equation before I find the antiderivative of it. So what I'm going to do is I'm actually going to, and I'll do this in 2 steps, I'm going to factor out 1/2. If I factor out a 1/2, I technically will have this. That reduces that. But I now see I do have another greatest common factor I can factor out of this equation. So I'm going to go ahead and do that. I can factor out a -3. And now I have this left to integrate. It's much easier to integrate, and all we did was do some GCF work. So now finding our antiderivative. And then we're going to evaluate it from 3 to 6. And then doing our work here, we should get it down to that we have 54 pi as our volume. All right, our last example that we want to do is number 33. And this is going to be where we're given this function. I'm sorry, this, and x equals 1 and y equals 0. And then it says we're going to rotate about x equals -2. So we're rotating about another axis. And this case, we're going to have an x equals, so it's going to be where x is -2. This is our axis of rotation here. And then it says if we follow through this region that it's all bounded by, it's basically this region, and we're bounded, and we're going to rotate around that other. So if this is the case, our equation for evaluating the volume now becomes instead of just 2 pi times x, it's going to be x plus whatever we shifted that axis of rotation, and then we'll have the f of x minus the g of x dx. So we're using this, and we're going to go ahead and set up that we're going from A to B, and we know we're going to be going from 0 to 1. So I'll bring my 2 pi out, 0 to 1. And now, instead of just x, it's going to be x, oops. In this case, it's going to be x plus 2. We are moving 2 further away. So we're going to further away. It's this case, then it's like if it's to the negative, to the left, we're going to add that distance. And if it were moving to the right, we're going to subtract that distance. So we're going to go ahead and then have this times our function, which is x squared dx. We need to go ahead and simplify this equation inside and get x cubed plus 2x squared dx, and then we're going to find the antiderivative of this. After all is said and done, we should be 11 pi over 6. Last thing I want to show on here in this video is in our textbook, if you want it on page 475, is a nice summary for the disc, washer, and shell methods. So it shows you a picture and it tells you about what axis. So here is integration with respect to x. Disc and washer method are about the x-axis. There's your formula. The shell method about the y-axis. We want to do parallel to the y-axis. Okay, shells are parallel. So then we have it in terms of x. So that's why it says about the x-axis, y-axis, but notice it says these two are with respect to x. So we have then, integration with respect to the y, so I keep moving this. And we have here the disc and shell method about the y-axis, and then we have the shell method about the x-axis. So the shells are parallel to the x-axis in terms of y. So that is a nice summary to have. You can print this page out at least and have that with you while you do your homework.